So first of all, let's talk about the plan for today. Today we first talk about lecture and then we are doing the lab. But today's lab is we're doing the lab 40. But the lab 40 is just preparing the solution for the titration lab. So we're not going to write any lab report, okay, for the lab 40. Instead, just preparing the solutions, okay. And once we finish the preparing the solution, we still have extra time, and then that's gonna be the time for finish your lab 30. Okay. Last time when we talk about lab 30, we just talk about how to solve the limiting reagent problem for the calculations for your lab report. But actually, it's also including some parts like a purpose, conclusion, and also the pre-lab question in the lab menu. So if you already finished that, then once you prepare the solution, you're done. Otherwise, you can finish that in the lab for the rest of the lab time. Are you clear? Okay. And we will have a quiz on next Tuesday. Okay, we will have a quiz on next Tuesday. All right. Yeah. Any questions? All right, so now let's just review what we learned last time. So last time we talked about specific heat equation. Q is equal to specific heat time mass of the object time the change of the temperature, which is the final temperature minus initial, okay? And we talk about the change of temperature could be a negative sign, okay? As long as if you have a higher temperature to the, if I have a low temperature to the high temperature, then if you have a high temperature to the low temperature, the final temperature, if it's lower than the initial, then this change of temperature will be the negative. It don't have to be always positive, okay? Yeah. Then we talk about this equation can be used to quantitatively measure how much heat that the object will gain or lose from based on the temperature change. Okay, yeah. And we also talk about some specific cases. If we have a hot object that drop into the cold water, then the hot object will lose the heat and the cold object will gain the heat. Okay, so we can set up equation like the heat that the metal lose should be equal to the negative sign of the heat that the water gain. The absolute value for the heat should be the same because we talk about, okay, heat cannot be destroyed. One thing is losing the heat, the other thing gonna absorb the exact amount of the heat. But they have a negative sign shows up here, then that means one is losing the heat, one is gaining the heat. And we talk about that. It really doesn't matter where you're gonna put the sign, okay? Either you put the negative sign on the heat of metal or you put the sign for the heat of water. That's really doesn't matter, okay? The matter is the heat of metal and the heat of water should have a negative sign in between, okay? Yeah, this is the important part because one is gaining heat, one is absorbing the heat, okay? Yeah, so now then we know, okay, we can rewrite the heat of metal or heat of the water by using the specific heat equation, C times M times final temperature minus initial temperature. Okay, and then we can set up a long equation just like this. And then we can use in this long equation to solve some of the case specific questions, right? And we talk about if the question gonna using this, and they should give your most of the numbers for each of the this unknowns, okay? They should only just left one unknown and then you can solve the problem, okay? And we talk about once you set up this equation and you plug the numbers in there, the leftover thing is the math problem. It's not a chemistry problem, okay? And then you have to, based on your math technique to solve the algebra, to solve the rest of the unknown, okay, to solve the rest of the unknown. So this is what we talk about for the specific heat. Okay, we talk about two different questions. One is hot metal dropping into the cold water. The other one is hot water dropping the cold water, generally doing the same thing, right? Only the concept is the heat, the hot object losing the heat, and the same heat will be absorbed by the cold object. Okay, so once you set up this equation, you can extend those symbols by using the specific heat equation. Then you can solve the problem. Okay, and also last time we talked about another concept, which is the enthalpy. Okay, we talk about enthalpy is actually a complicated concept, but in Chem 1 we only talk about the change of enthalpy. Okay, we only talk about change of the enthalpy, and in general, change of the enthalpy is just the heat when this reaction is under the constant temperature and a constant pressure. Okay, so in most of cases, enthalpy, the change of the enthalpy is the heat. Okay, so at least in our current situation in Chem 1, we just assume the change of the enthalpy is the heat. Okay, so that is why anything that belongs to heat is belong to also will shows in the change of the enthalpy. The change of the enthalpy could have a sign because heat has a sign. If we talk about the positive sign for the change of enthalpy, then that means the system gain the heat, and then that's going to be the endothermic. If there's a negative sign, that means the system lose the heat, then that's going to be the exothermic reactions. Okay, exothermic reaction. And we also talk about, doesn't matter what kind of reaction, as long as we have a reaction, and then they are always come with a change of the enthalpy for this reaction. Or you can talk about is the heat of the reactions, right? Doesn't matter is endothermic. For the exothermic reaction, we're going to produce the heat. So you're going to have a heat. The heat will be a negative sign, which is it produces the heat out. If it's an endothermic reaction, then this heat will be a positive sign because they gain the heat. So it doesn't matter whether it's endothermic or exothermic, they always has a delta H, the enthalpy, change of the enthalpy with the reactions. Okay, for example, this one we write as a negative, this reaction is a negative 100 kilojoule. And this negative 100 kilojoule means, first, this guy means is exothermic reaction. And this, and the 100 kilojoule means if we have a 1 mole of A reacted with 1 mole of B to form 2 moles of C, and meanwhile, they are going to produce 100 kilojoule of heat, okay? And this is really depends on the coefficient. So this equation has a coefficient 1, 1, 2, and then the heat is negative 100. So this is the relationship between moles of the object and the heat. Okay, so that's why you can base on this to figure out the stoichiometry, to figure out the heat and the moles of the object. Okay, yeah, so this is another kind of the stoichiometry. Okay, and we talk about for these cases, you can use two different ways to solve the problem. Either you're using stoichiometry just based on you have an unknown and your time conversion factor between the heat and the moles of the object, and then you can figure out. Or you just based on the ratios, right? You can base on the ratio to figure out the unknown. For example, if we have a 4.3 moles of A, how much heat that we can produce? Well, the setup is just based on what we know. 1 moles of A will produce negative 100 kilojoule of the heat. Well, so now we have 4.3, how much heat we can produce? The ratio, 1 moles of A versus 4.3 of A should be equal to the ratio that's negative 100 kilojoule versus the question mark. Okay, and you just need to try to figure out what is the question mark. based on the equation like this. This is an algebra question. Okay, so if you're good at on this way, you go ahead to doing this way. Okay, to solve what is the heat that you're gonna produce for 4.3 moles of A. Okay, yeah, we also do one of the questions to solve the problem. Okay, today we'll continue to talk about the stoichiometry involved in the heat. Okay, involve heat. Let me grab my stuff. Let's just take a little break. And also raise your hand if you do not have the permission. Okay, so let's turn to the question number 3 in page 4. Question number 3 in page 4. And this one, this is talk about, okay, talk about during an experiment, 10 grams of the ethanol is completely burned in air to release CO2 and water as shown in the following equations. During the combustion, 296.6 kilojoule of the heat is released, and asking for what is the molar enthalpy of the combustion. Okay, molar enthalpy of the combustion. So let's first set up this equation. Ethanol react with 3 moles of the oxygen to form CO2 and water. Okay, so now let's see what we have. We have is a 10.00 gram of the ethanol, and then the enthalpy that they produce is so 10 gram of the ethanol produce 296.6 kilojoule. Well, this question didn't write the sign. They just gave us as a produce 296.6 kilojoule. My question is it exothermic or endothermic for this reaction? What do you think? This is exothermic. Okay, why? Because the question talk about is they're going to produce or release that much of heat. Okay, you produce or you release that much of heat, that means obviously the system is losing the heat. So this is an exothermic reaction. So you're gonna have a negative sign, although the question didn't show, but then we have a negative sign out here. Or you see the question also asking for, yeah, so this guy should have a negative sign. But this is how much heat? This is not 1 mole, you see? We are using 10 grams of the ethanol and we produce that much heat. In another word, this much of heat is not from 1 mole of ethanol. It's from 10 grams of the ethanol, okay? So obviously, first of all, we need to figure out how many moles of ethanol that produce that much heat? Because here we all talk about the moles. We're not talking about a gram. Okay. So first you're gonna convert that to the moles. Okay. So you're gonna have 110 grams of the ethanol divided by molar mass of the ethanol to figure out the mole, which is divided by 64 grams per mole of the ethanol. Then you got the 10 divided by 46, and you got a 0.2174. 0.2174 mole. Okay, so then we're gonna change this. That means, okay, if I use up 0.2174 moles of ethanol, we're going to produce that much of heat. Okay, yeah. And then let's look at what's the question asking for. The question is asking for enthalpy of the combustion. Okay, so the molar enthalpy of combustion. So we haven't talked about this. And here, let's see. It talk about molar enthalpy of combustion. That means if we have 1 mole of the ethanol, how much heat that can produce. Okay, so molar heat of the combustion, the generally is talk about the combustion reactions. So the combustion reaction is always has a hydrocarbon as reacted with oxygen to produce CO2 or water. Okay, so here we're talking about if we have 1 mole of this object to react with the oxygen, how much heat it can produce. So this is by definition. Okay, so that is why the unit is a kilojoule per mole. So that means 1 mole of this object got reacted, combusted, how much heat it can produce. And then what we write over here? Well, obviously they talk about, so now the question asking for 1 mole of the ethanol, how much heat that they are going to produce. That makes sense, right? Okay, then that's easy to set up. Well, is the easiest way is just using the ratio. 0.2174 moles of the ethanol produce that much heat. Then how much 1 mole? So 0.2174 divided by 1 should be also equal to the ratio for this much divided by the question mark. And the question mark is what you need, right? We're only just for 1 mole, how much 1 mole of heat. So the question mark will be just equal to negative 296.6 kilojoule and time 1 mole of the ethanol and divided by 0.2174 mole. That's it. Okay, so now you will see negative 296.6 times 1 divided by 0.2174. We got negative 1364. Okay, so negative 1364 kilojoule of the heat, the kilojoule. Okay, so that is the kilojoule. Okay, that is the kilojoule. And then that is going to be the answer because the question only just give us as a 10.00 gram. So it's 4 feet. The answer will be 4 feet over here. Okay, yeah, that makes sense. Okay. So now please go ahead to work on the question number 5. Okay, work on the question number 5. Okay, so let's review this question. Here. So first of all, we're gonna balance this equation, and then let's see what the question gave and what's the question asking for. They talk about we have a 1.00 mole of the methane. Okay, yeah, and this methane will produce the CO2 water, and meanwhile they are going to release the enthalpy. Okay, release the heat, and the heat, how much is released, is 802 kilojoule per mole. You see, it write per mole. The per mole here, that means if I have a use of 1 mole, because you see this is a stoichiometry, 1 mole of this is going to produce that much of heat. Okay, so this is a per mole mean. Okay, 1 mole of the methane will produce that much of heat. So you don't have to write this. And also this is a release. So it's exothermic. You have a negative sign. So 1 mole of the methane produce that much of heat. Okay, then let's see. Here talk about 3.00 mole of the oxygen react with a stoichiometric quantity of methane. What is the heat for the reactions? Well, this is awkward because it's the question gave us 1 mole of the methane produce that much of heat. It didn't talk about oxygen, but do we know? Remember last time we talked about, okay, so if we talk about reaction A plus B to form 2C, and we have enthalpy reacted, okay? If we, the whole thing, the reaction, if this is a negative 100 kilojoule, what does that mean? That means 1 moles of A react with 1 moles of the B to form 2 moles of the C, and the heat is 100 kilojoule. Okay, it's not just talk about 1 mole of A. We also talk about this because the coefficient. Look at the coefficient. 1, 1, 2. Okay, so the same thing over here. We're not in this case. This talk about 1 mole of the methane can produce a heat. Although they didn't talk about the rest of others, but they default telling us they need 2 moles of oxygen. If we use up 2 moles of oxygen, we can also produce that much heat. To finish the whole complete reaction, you need 1 moles of methane, 2 moles of oxygen. Then they're going to form 1 moles of the CO2 and also form 2 moles of water. And during this process, they are going to produce that much heat. Are you clear? Okay, although the question didn't talk about, okay, the 2 moles of oxygen will produce that much heat, but this is based on the stoichiometry. This is what we shows in the question, in the equation. All right? Okay, so now then that's gonna be more clear. The question, based on the stoichiometry, we know 2 moles of the oxygen will produce that much of heat. So now the question asking for 3 moles of oxygen, how much heat they can produce. Then what we do? Well, 2 versus 3 should be equal to that much heat versus the question mark. That makes sense, right? Then the question mark will be just equal to negative 802 kilojoule and times 3.00 moles of oxygen divided by 2 moles of the oxygen. Then you can solve the problem. 802, negative 802 times 3 divided by 2. It's a negative 1203. Negative 1203. But the question, you see, the question only gives us 3 sig figs. So you need to convert that to the 3 sig figs. So the question, this answer should be, you cannot write a 1200. 120 only just 2 sig figs. So you have to change that to the scientific notation. That's going to be 1.20. times 10 to the 2, 10 to the 3. Okay, so then that's going to be a 3 feet for this question. Okay, yeah. So this is the tip. If the question didn't talk about the rest of the others, but actually based on the stoichiometry, based on the chemical reactions, its default is already showing you how much most of these others will produce that much heat. Because if you have to complete the whole reactions, then you can release that much of heat. That makes sense, right? And one more thing I need to mention is, okay, some of the questions say how much heat they are going to release. We can see they have a 1.20 times 10 to the 3rd kilojoule of the heat is released or produced. Okay, so I didn't write negative 1.20 times 10 to the 3 kilojoule of heat is released, because the released and produced is meaning they have a negative sign. That makes sense? Okay, yeah. So if the question asking for how many heat is released, then you don't have to write the negative sign over here, because it already shows this is exothermic reactions. Okay, yeah. So let's do one more question. Okay, yeah. Let's turn to the page 5, question number 7. Okay, question number 7. So now we have a 25 Celsius. At 25 Celsius, the delta H now for this reaction is a negative 598.8 kilojoule per mole of the lithium oxide. Okay, so based on that reaction, then the question is, what mass of the lithium should be reacted with excess oxygen in order to release 150 kilojoule? Well, this one is even complicated. Let's see. So this one, 4 moles of the lithium react with oxygen gases, and then it will form 2 moles of the lithium oxide. This is solid. Okay, so now, and also they're going to have an enthalpy shows up here. And let's see what's the question asking for. What way the question have? The question have, they are going to release negative 598.8 kilojoule of the heat per mole of the lithium oxide. So what does that mean? Okay, so now we're not talking about lithium. We're not talking about oxygen. Here now we're talking about product. Okay, we're producing that much of heat if we form 1 mole of the lithium oxide. That is the relationship. See, look at this. It's the delta H for this reaction is negative 598.8 kilojoule per mole of the lithium oxide. It's not talking about the per mole of the lithium. It's not talking about per mole of oxygen, but it's talking about per mole of the lithium oxide. In another word, is that here is talking about if we form 1 mole of the lithium oxide, they're going to produce that much of heat. Make sense? Right? Okay. So now, but the question is asking for how much lithium that we are going to do if we produce 150 kilojoule of the heat. The question is asking for lithium. Okay, then what we do? Well, the easiest way you do is first you need to, changing the conversion a little bit. Okay, so now we only know 1 mole of the lithium to produce that much heat. Okay, so now how about 2 moles of lithium? If we have a 2 moles of lithium, how much heat we can produce? Okay, the question, the ratio in the stoichiometry is a 4, 1, 2, right? 4 versus 1 versus 2 and produce much heat. Now we try to make a link. So it's easier just to convert the 1 moles of lithium to 2 moles of lithium. Then it will match to the coefficient, right? So if we have a 2 moles of lithium oxide, how much heat do we need? Just 2 times this, right? Yeah, right. So now if we have 2 moles of the lithium oxide, then we're going to produce 598.8 times 2. So negative 1197.6. Negative 1197.6. Okay, kilojoule. All right. So now that's going to be easier because it's matched to the ratio. If we have a 2 moles of the lithium that form this much, that means they are going to use, based on stoichiometry, they're going to using 4 moles of lithium and also using 1 moles of oxygen, then they can produce 2 moles of the lithium oxide. And also they're going to produce that much heat. So now you make a link between moles of lithium and the heat. That makes sense? Okay, now you got the moles of lithium and the heat, you see? Now 4 moles of lithium will produce that much heat. And meanwhile, they're going to form 2 moles of the lithium oxide and also going to produce much heat. Okay, so 4 moles of lithium plus, oh, sorry, that should be 2. Should be 1. 4 moles of the lithium reacted with 1 mole of oxygen to form 2 moles of the lithium oxide, and meanwhile we're going to produce that much heat. Now then you can solve the problem. 4 moles over the question mark should be equal to the heat over the heat that we have. The question given is a negative 150 kilojoule of the heat, and then you can, based on this ratio, to figure out the question mark, which is how many moles of the lithium that can produce negative 150 kilojoule of the heat, right? So 4 mole divided by the question mark should be equal to negative 1197.6 kilojoule and divided by negative 150 kilojoule. Okay, so now the question mark will be just equal to 4 times negative 150 kilojoule divided by negative 1197.6 kilojoule. Okay, so now you will got the moles of the lithium. 4 times divided by 1197.6. So 0.501. 0.501 mole. Now we got the mole of the lithium, but the question is asking for mass of the lithium. It's not asking for the mole of the lithium. So this is a mass of mole of lithium. So now if you want to get the mass of lithium, then what do? You can time the molar mass, right? Mole of the lithium, you time molar mass of the lithium, which is 6.0 941 gram per mole of the lithium, then you got the mass of the lithium, 0.501 times 6.941, and you got 3.777. Okay, 3.477. 477, and this is in gram. And if you double check the Siegfried, just like you know, 25 Celsius, the temperature usually is not used in this stoichiometry. Okay, so the number they actually only give is just a negative 598.8 and 150. So 150 is 3 Siegfried. So the answer will keep 3 Siegfried. So that's going to be a 3.48 gram. 3.48 gram. I know this stoichiometry is a trick, okay? But as long as you understand this process, okay, the mole, the heat is not just linked to one object. It's going to be linked to the whole equations. Okay, yeah. If we have one thing linked with the heat, the other objects in the reactant or the product, the moles of this will also linked with the heat. Any questions? Good or bad? Or okay, yeah. So you definitely need to practice. Okay, we still have some of the practice over here, and you need to work on this. Okay, yeah. And again, I will do some during the class, probably next week, next Thursday, and we will using the lab time to do another catch-up practice time. Okay, yeah. Okay, so this is talking about the stoichiometry. Okay, stoichiometry. The next part, we're going to talk about how to manipulate the chemical reactions, okay, with the heat. How to manipulate the chemical reactions. How to manipulate. I don't know what is how to write the material. Well, anyway, so we're going to talk about the chemical reactions can be changed with the heat. Okay, so this is the first thing we need to talk about. Okay, so for example, if we have the reaction A plus 2B and to form 3C, and we have the change of the enthalpy is negative 100 kilojoule. Okay, so we have this equation, and this equation can be changed by multiplication. So if we multiply a certain number, for example, we multiply by 2 on this equation, is working. Okay, yeah, and just to let her know, in thermochemistry, the coefficient could be fraction, could be not simplified. Okay, yeah. So if we multiply this whole equation, it will become 2A is reaction with 4B and to form 6C. And meanwhile, the enthalpy change for this reaction will also double. It become 2 negative kilojoule. Okay, become 2 negative kilojoule. So this is the one thing you need to be careful. Okay, so if you manipulate time 2 on the equation, the heat will also double. Okay, so the reason is for the first equation is talk about 1 mole of A to react with 2 moles of B, and then they're going to form 3 moles of C. And meanwhile, they're going to produce 100 kilojoule of the heat. But if you're talking about this reaction, this become 2 moles of A and 4 moles of the B to form 6 moles of the C. So obviously, you're double the moles of each of the reactants and form double the moles of the product. And the heat of this reaction will also double. That makes sense, right? Yeah. So this is why you need to double the heat of the reaction, because those are not the same equation anymore. They changing the amount of the heat. Okay. So if you're time the coefficient for each of this, you're gonna also time the same amount on the heat, on the enthalpy of the heat. Okay, this is a very important part. Okay, and this is a multiplication. So if you're time 3, doing the same thing. If you're time 4, doing the same thing. And but if you're divided by the same thing, it's also the same. Okay, so if you're divided by 2 on this equation, then it will become 1 over A, 1 over 2 A, 1/2 A plus 1B to form 3/2 C. And the enthalpy of this reaction will also decrease. You're gonna time 1/2. Okay, so that's gonna be negative 50 kilojoule of the heat. So in the thermal chemistry, those fraction as a coefficient is doable. Okay, is reasonable. Okay, so it's allowed. So you don't have to. I mean, you don't have to worry about the fractions. This is doable. This is allowed for the thermal chemistry. Okay, and in this case, that means we have a 0.5 moles of A react with 1 moles of the B, and meanwhile to produce 1.5 moles of the C, and meanwhile this is going to produce 50 kilojoule of the heat. Okay, yeah, so this is special for the thermal chemistry. You're gonna multiply a certain number, the heat will also multiply. If you're divided by a certain number, the heat will also need to divide by a certain number. Okay, yeah, so this is how you manipulate these equations. Next part is also manipulate. Okay, so what if you reverse this equation? Here we have A plus 2B to form 3C. But if you reverse this reaction, well, if you reverse the reaction, become 3C to form A plus 2B. Okay, so now you reverse this equation. Okay, then what are you going to do? The enthalpy of the heat, the sign will also reversed. Okay, the sign will also reversed. Original is a negative 100 kilojoule, then it will become a positive 100 kilojoule. Okay, so that means if you reverse the reaction, originally is an exothermic reaction, but if you reverse this reaction, it will become endothermic reactions. Okay, so exothermic reaction and the endothermic reaction generally is coupled. Okay, if the forward reaction is exothermic, but if you're then the backward reaction should be endothermic. Okay, should be endothermic. Okay, so the sign will be changed. Okay, you didn't do anything, but the sign will change. So this is a 3 different way to manipulate the equations, the chemical equations. If you multiply a number for the coefficient, and then the enthalpy of the heat, enthalpy of the reaction or heat of the reaction will also multiply the same number. If you're divided by the number on the coefficient, the enthalpy of the reaction will also divide by the same number. And third one is if you reverse this reaction, and the sign of the heat will also be reversed. Okay, will also be reversed. So this is the how to manipulate the equations. How to manipulate equations. Okay, yeah, and let's take a break. Okay, let's take a break. Okay, so let's come back. The last manipulation is addition. Okay, it's addition. So if you have two equations, like so for example, A plus 2b and to form 3c. And the enthalpy of this reaction should be negative 100 kilojoule. Well, we have another equation. Let's say the equation is 3a plus, okay, 3a plus 1c, no, not 1c, 1d to form and 3b, okay, and the enthalpy of this reaction is positive 50 kilojoule, okay. Now we have the two equations over here. One equation is a plus 2b to form 3c, and the enthalpy is that much. The second equation is, this is a d, okay, 3a to plus 1d to form 3b, and the enthalpy is this. And then the multiplication is, okay, so if we add those two equations, okay, then what happens? To adding the equation, what you need to do is everything on the left side of the arrow, you add them together. Everything on the right side, those stuff, you add them together. In between, it's still arrow, okay? So everything on the left side, that's going to be just a plus 2b and the plus 3a and the plus 1d, okay? And then they're going to form 3c plus 3b. And meanwhile, when you add up the equation, this enthalpy will also add up together, okay? The enthalpy of this new equation. Now, you see, we are having the new equation. This new equation is not the previous one, it's a new equation. The new equation, the enthalpy of this new equation will also add up those two. This is a negative 100, this is a 50, so the result is going to be negative 50 kilojoule. That makes sense, right? Yeah. So you add them together, the new equation will be has a new enthalpy of the reactions. But the point is, I mean, you have to calculate a little bit to make this equation simplified. Okay. So now a plus 3a, so you have a 4a, right? You have 4a. And the plus 2b and the plus 1d to form 3c plus 3b. Well, then you see, okay, now we have a 2b over here and we have a 3b over here. Then what are you going to do? This is an equation, right? You can get rid of those. The 2b will be canceled out with the 3b. So the 2b will cancel out with 3b. The leftover on the right side, only just 1b left over. Does it make sense, right? Does it make sense, right? Okay, yeah, so now we have a 3b, then instead of 3b, we become just a 1b. Now, and then we can double check, is there anything that we can cancel out? Looks no, right? Then you can rewrite the equation. The final equation is just a 4a react with 1d. And then they're going to form 3c plus 1b. And then the enthalpy of this new equation will be negative 50 kilojoule. Will be negative 50 kilojoule. Okay, so now this is a completely new equation. Completely new equation. Okay, and also based on the modification, based on the previous calculation, we also figure out what is the enthalpy of this reaction for the new equation. Okay, yeah, and this process we give it a name. It's called the Hess's law. Okay, we give this process. If you add up two equations, and then the enthalpy will also add up. This is the concept we give it. It's called the Hess's law. Okay, this is called the Hess's law. And looks like the Hess's law is pretty straightforward. But when you really apply that into the real situation, it's become very complicated. So that is why I'm going to spend the rest of the time to emphasize how do we using the Hess's law to solve the real questions, So let's turn to the page 8. Okay, let's turn to the page 8. And let's look at the question number 2. I mean, this question number 2 is a conceptual question. So it's easier. So now for this is a page 8, question 2. Now we have 3 equations, A plus B to form C, and the enthalpy of this reaction is -35 kilojoule per mole. Okay, and the second one is A plus D to form E plus F. The enthalpy of this is equal to +20 kilojoule per mole. Last one is F to form C plus E. Okay, the enthalpy of this will be equal to +15 kilojoule per mole. Okay, so now we have 3 equations, 1, 2, 3. Now what we do? The question is asking for what is the enthalpy of this equation, 2A plus B plus D to form 2F. Okay, so what is enthalpy of this new equations? Well, what is the enthalpy of this new equations? Well, then what are we gonna do for this question? So again, if you add up those equations together, obviously it's not a new equation, just to let you know. Okay, you cannot just simply add those 3 equations together to make a new equation. No. Okay, so you have to manipulate each of the equations. Some of the equations you don't have to manipulate, some of them you do. And then you add up the modified equation together to make a new equation. So that is a purpose. Okay, that is a purpose. And also you have to check everything and to either modify those equations and then add everything together to make a new equation. Okay, so my hint is you have to, first of all, to make this new equation my way, this is the tips that I summarize. Okay, yeah, you cannot find anywhere to find this. Okay, you have to find a unique component for each of the equation and then modify based on the unique component to modify these equations. Okay, so what does that mean as a unique component? The unique component is unique. Wait, thank you. Okay, unique component. Okay, so the meaning of the unique component, that means this component or this species is only shows in one equation. It's not shows in, for example, 1, 2, 3, we have those 1, 2, 3 equations. A is not a unique component because A shows in both equation 1 and equation 2. So that's not unique. Okay, yeah. And C is also not unique because C shows in both 1 and 3. So C is also not a unique component. The only B is a unique component for the first equation, because B is only shows in the first equation. It's not shows in the 2, it's not shows in the 3, but it shows in the B, the final equation. Okay, it shows in the final equation. So that's why you're gonna look at the B, and then based on the B to modify the equation and to match the final equation. Again, eventually our purpose is we're going to modify each of the equation and then add up each of the equations to make the final equation. Then you can think about the final equation has a B. Only A has the first equation has a B. So since this B already on the left side, if we add up this equation, we should have one B on the left side. That makes sense, right? So that means in the first equation, we don't have to modify anything, right? We don't have to time 2 on this. We don't have to time 3. If we time 2, then we should have a 2B on the left side. But obviously, we only have 1B on the left side. So for the first equation, you even don't have to do anything. You just keep as it is. So that is why you need to find the unique component, and then based on the coefficients of this to modify what you need. Okay, yeah. So I know you're still confusing. Then let's just keep doing this. Then you probably will know what does that mean. So for the first equation, you don't have to modify. You just keep as it is. Then the first equation is just A plus B to form C. And the delta H will be just still, again, it's negative 35 kilojoule per mole. Okay, then let's see if there are any unique component in the question number, the equation number 2. Well, A is not, right? It shows this. D looks like is. Yeah, D is only shows in the question number 2, right? The equation number 2. And if you see E is, oh, this is E, I think. F2, this is E. Okay, this is E. Okay, so E is not unique. It shows both on the 2 and the 3. F also not unique. So we, how to modify the equation 2 is really depends on the unique component D. Okay, and if you look at, we also has a 1D on the left side. Now we already have 1D on the left side. So again, we don't have to modify this equation anymore. So we just write as it is. A plus D to form E plus F. And the delta H for this equation is plus 20 kilojoule per mole. Okay, and let's look at the equation 3. Do we need to change anything? Well, F, C, and E, all of those are not unique components. Okay, so we cannot, based on the coefficient, based on those to modify this equation. But we can just first, but we can based on the, we already modified those first 2 equations. Let's see what if we add up those 2 equations, what we can have. Once we add this equation, we got 2A, and we got a B, and plus D to form C plus E and plus F. And the delta H should be the addition of these 2. That's gonna be negative 15 kilojoule per mole. Okay, so this is the second equation. If we add up those modified equations, and we got those 2 equations, these new equations. And let's see what is difference. Well, at least we have something similar. We have a B, we have a D, but we have a 2F on the right side. but this question only have one F. So what we do? I mean, definitely the other F should come in from the third one, right? The other F should come from the third one. So this, we need one more F on the right side, but we have one more F on the left side for this equation. Then what we're gonna do? You're gonna reverse this equation, right? So let's see. If we reverse this equation, it becomes C plus E and to form F. So the delta H for this equation is just equal to negative 15 kilojoule per mole. Okay, so now let's add up. So now 1, 2, 3 equation are all modified. Then let's add up final equation again. Let's see. We have a 2A plus B plus D plus C plus E. And then they're going to form C plus E plus F plus F. Okay, so now you see, if you look at over here, there are some common things on both sides. C and C can be canceled. E and E can be canceled. So the leftover is just 2A plus B plus D to form 2F. And the delta H for this equation is just the addition of those two, which is negative 30 kilojoule. And then let's review. Is this equation exactly the same as for the Ricard equation? Yes. So that is why the enthalpy of this reaction is negative 30 kilojoule. Yeah, it's negative 30 kilojoule. Okay, yeah. I know this is probably your first time to see this. You never see this in the high school, I think. Okay, yeah. So you definitely need to do the practice. Let's do one more practice. Okay, let's do one more practice. And let's turn to the page 8, still page 8, question number 3. Okay, page 8, question number 3. So this is the real equation, right? Those are, we have a real equations over here. Sulfur plus oxygen to form 2SO2. Delta H is negative 296.8 kilojoule. Okay, hydrogen reacts 1/2 of the oxygen to form water. Delta H is negative 285.8 kilojoule per mole. The last one, hydrogen plus sulfur to make H2S. Delta H is equal to negative 20.6 kilojoule per mole. Okay, so for this one, we have a 3 equation, 1, 2, 3. Okay, 1, 2, 3. And then the question is, what is the enthalpy for the following equation? What is the enthalpy for the following equations? Again, the purpose is to modify 1, 2, 3 equations and then add up those 3 equations, modify the equation to make a new equations. And then let's find the unique component for each of these equations. Okay, so unique components is only shows in this equation. It's not shows in the other equations. So let's see. Looks like a sulfur is not unique because it shows on both equation 1 and 3. Oxygen is not unique because it also shows in the 1 and 2. So SO2 is a unique. This guy is unique. It only shows in the first equation. Okay, and let's look at the second one. Which one is a unique? Hydrogen is not unique because it shows in both equation. Water is unique. Good. And the H2S is unique. So now we find the unique component for each of this equation. Then we're going to just based on the unique component to modify unique component and the coefficient of this unique component in the final equation to modify this equation. For example, the final equation, we need 2 SO2 on the right side. But the point is we only have 1 SO2 on the right side. You can think about it. If we don't do anything, we just add up this equation, we should only have 1 SO2 on the right side. That makes sense, right? So what are we gonna do? Then definitely we're gonna time 2 on this equation. So we can have a 2 SO2 on the right side. So you're gonna modify this equation, become 2S, become 2 oxygen, and to form 2 SO2. And then the enthalpy will also doubled. It become negative negative 593.6 kilojoule. Okay, yeah, so this is what we talk. And the next one, we are based on water. Where's the water over here? We have 2 water on the right side. Again, we have to time 2 to get 2 water on the right side, since we need to add them together. So the second equation, we also need to modify by 2. So we have a 2 hydrogen and the time. So this is 2 hydrogen and 1/2 time 2. So we got a 1 oxygen and to form 2 water. And the enthalpy of this reaction also need to double. Then we got is a negative 571.6 kilojoule. Make sense, right? Yeah. And then let's look at the next one. Last one is H2S. Okay, H2S is unique, but where is H2S on the end? We have a 2 H2S on the left side, but right now we only have 1 H2S on the right side. So remember, if we want to add up those 3 equations, if we didn't do anything, we should have a 1 H2S on the right side. But this is not what we want, right? What we want is 2 H2S on the left side. So we need to do 2 different modifications, right? First of all, we need to time 2 on this equation. And second of all, we need to reverse this equation. So we can have a 2 H2S on the left side. Does that make sense, right? Okay, so now what we do? We need to time 2 and reverse. So I'm combining them together. So we should have a 2 H2S and to form 2 hydrogen and plus 2 sulfur. And then you're going to do the same thing for the enthalpy of these reactions. So first, we need to time 2 on this. Then you got 41.2. And then we're gonna reverse this equation. So you change the sign. So you should have a positive 41.2 kilojoule. Okay, so now you already modified all the equations. Then what you need to do is add up the equation. I guarantee if you make the modification correctly, you add them together, you should get the final equation. Okay, I guarantee. Okay, so let's see whether it's correct or not. Again, everything on the left side, you add it on the left side. Everything on the right side, you put on the right side. So 2s plus 2 oxygen plus 2 hydrogen plus 1 oxygen plus 2 H2S. Then they're going to form 2 SO2 plus 2 water plus 2 hydrogen plus 2S. Okay, yeah. So now this is what we add up over here. This is what we add up. And then let's see if there are any common things on each side. Yes, 2 hydrogen, and you cancel with 2 hydrogen over here. 2s and the 2s is canceled. Then let's see. Then there's no other common molecules. Okay, then your 2 oxygen plus 1 oxygen, you got 3 oxygen. And you plus 2 H2S. Then they are going to form 2 SO2 plus 2 water. Well, this one is exactly the same, just shows for the target equation, right? So the enthalpy of this equation, again, that's just the add up of those 3 equations. Then you will see that's gonna be negative 593.6 plus negative 571.6 and plus 41.2. Okay, so if you add them together, the answer should be, okay, just 1124. Okay, the answer will be negative 1124.0 kilojoule. Okay, yeah, negative 1124.0 kilojoule. Okay, yeah. So this is how we solve this kind of a problem, Hess's law. I know this is some of you probably is just like this, you got it. But some of you probably you need to do the practice and then understand how to solve the problem. I'm giving you the technique, the skills, okay, or tips to solve this problem. Again, in this question, page 8, page 9, page 10, page 11, those are all Hess's law questions. Okay, and if you want, you can find tons of the Hess's law questions on the website. Just search Hess's law practice question. There's a lot. Okay, yeah. So you definitely, if you want to do practice, you can have a lot to practice. Okay, yeah. And again, next week, I guess it's next Thursday, we will just use in the lab time to do the practice. Okay, use the lab time to do the practice. Okay, on Monday, on Tuesday, we will have a quiz. And one of the quiz is involving Hess's law. Okay, one of this is involving the Hess's law. Okay, yeah. The other one is a stoichiometry. It's a stoichiometry. Probably just 2 questions because those 2 are pretty time consuming. Okay, yeah. Again, quizzes is not for, I mean, I don't want you let you down, but you need to, I'm kind of pushing you to do the practice. Okay, yeah. If you don't understand those 2 concepts, I will find some of the videos online and send it to you so you can review those questions. Okay, yeah. So let's move to the lab.